There is a home that costs $300 to build, $0 to heat, and has survived tornadoes, wildfires, and a 5,000-pound bomb blast. FEMA certifies its resilience. The structural principle behind it has been proven for nearly 20,000 years. Yet across America, you can't get a mortgage to own one, and the reason has nothing to do with engineering. In the heart of central Ukraine, long before the first bricks were laid in any city, humans built shelters that defied the odds of their time. At Medjugorje, archaeologists uncovered 4 structures dating back nearly 18,000 years, some of the oldest known buildings on Earth. These were not simple lean-tos or piles of brush. Each shelter measured between 130 and 260 square feet, large enough to house entire families through brutal winters at the edge of the last ice age. The builders used what the land provided. Mammoth skulls and long bones formed the foundation, set upright in the frozen ground. Massive tusks arched overhead, creating a self-supporting curve that channeled the weight down and out, not unlike the archways of later civilizations. Over this skeleton, they draped animal hides or birch bark for insulation, then weighed everything down with more bones to hold against the wind. These domed dwellings were more than temporary camps. Evidence shows at least one was occupied for over 4 centuries, sheltering generations through relentless cold. Inside, the remains tell a story of daily life: flint tools, pits filled with artifacts, and signs of communal work. 5 or more people lived, worked, and survived together within each curved shell. The design was not a matter of style, but survival. A structure that could stand against the elements using only the materials at hand. Long before the first city walls, the logic of the dome had already taken root, proving that curved forms could offer lasting protection where nothing else could. In the heart of ancient Rome stands a structure that has outlasted empires, earthquakes, and centuries of change: the Pantheon. Completed around 125 AD during the reign of Emperor Hadrian, its dome still holds the record as the world's largest unreinforced concrete span, stretching 142 feet across. No steel or modern reinforcement supports its mass. Instead, Roman builders relied on a careful mix of volcanic ash, lime, and graded aggregates, creating a concrete that grows lighter toward the top. The dome's thickness tapers from over 21 feet at its base to just under 4 feet near the oculus, a central opening nearly 30 feet wide that floods the interior with light. For nearly 1,900 years, the Pantheon has endured floods, invasions, and the constant tremors of a restless Earth. Structural engineers have studied its catenary curve, a shape that channels the weight of the dome into pure compression, pushing forces down and out rather than risking cracks or collapse. The 5 rings of recessed coffers carved into the ceiling not only lighten the load, but add stiffness, strengthening the shell without extra material. Even today, the Pantheon's concrete shows self-healing properties, with minerals forming new bonds that close micro cracks over time. The survival of the Pantheon is not a matter of luck or legend. It stands as proof that the logic of the dome, curved, seamless, and built for compression, can produce buildings that last for millennia. Roman engineers understood these principles in stone and mortar, setting a benchmark for durability that modern builders still measure against. In the mid-1970s, 2 brothers from Shelley, Idaho, David and Barry South, set out to solve a problem that had dogged farmers and builders for decades: how to create a building that could shrug off the worst weather, hold steady temperatures, and last for generations. Their background wasn't in high architecture or academia. David ran South's Incorporated, a company known across the Northwest for insulating potato storages with polyurethane foam. Barry worked alongside him, hands-on and practical. The South saw firsthand how foam could transform a drafty shed into a stable, efficient vault. But they wanted more than a better barn. They wanted a new kind of structure entirely. In 1976, the brothers filed for a patent on what they called an inside-out construction method. Instead of building walls and roof the old way, they would start with an inflatable form, an air form, anchored to a concrete footing. The process began with a blower, inflating the form into a smooth, curved shell. Then, working from the inside, they sprayed a layer of urethane foam against the air form, creating both insulation and a base for reinforcement. Over that, they attached welded wire mesh, and finally, they sprayed shotcrete, concrete applied at high velocity until the shell was several inches thick. The result was a seamless, monolithic dome, strong enough to resist wind, fire, and time itself. Their first full-scale prototype went up in Shelley in April 1976, a 105-foot diameter, 35-foot tall dome designed for potato storage. It was built using a zipper-sealed air form, a drawstring tie-down, and just 2 inches of air pressure to hold the form steady. Patent number US, Patent 4155967, was awarded in 1979, securing their claim to a process that would soon be tested by more than just Idaho winters. David and Barry's invention wasn't just a technical breakthrough, it was a leap of faith, born from the conviction that buildings could be both simple and nearly indestructible. 5 steps define the monolithic dome build, each one a departure from conventional framing. It starts with a circular concrete ring beam poured directly onto a prepared foundation. This ring anchors the structure and distributes loads evenly, eliminating weak corners found in box-shaped buildings. Next comes the air form, a tough, flexible fabric shaped to the desired dome profile. Once attached to the ring beam and sealed, a blower inflates it like a giant balloon, creating a smooth, continuous surface that sets the dome's curve. With the air form pressurized, workers move inside to spray 2 to 3 inches of closed-cell polyurethane foam directly onto its interior. This foam locks in the air form's shape and forms a seamless layer of insulation, typically rated at R20 or higher. The foam's placement on the outside of the future concrete wall means the heavy shell will act as thermal mass, buffering temperature swings so effectively that interior fluctuations rarely exceed 5 degrees Fahrenheit, even in extreme weather. Next, a grid of steel rebar is installed, suspended from the foam using custom hangers or mesh. This reinforcement forms a cage that resists tension and holds the coming concrete in place, matching the dome's curve precisely. Finally, shotcrete, concrete sprayed at high velocity, is applied in layers over the rebar, building up a shell several inches thick. The result is a seamless, monolithic structure where the shape itself is the secret. A catenary curve proven by centuries of engineering channels all forces into pure compression. Wind, snow, and even tornado debris are deflected and absorbed, not resisted by flat planes. The entire process, from inflation to final curing, can be completed in weeks, not months. What emerges is a building with no joints, no roof seams, and no thermal bridges, a shell engineered to last centuries, not decades. Claims about the monolithic dome's strength and efficiency have been tested again and again, both in the lab and in the real world. FEMA rates these domes as offering near absolute protection from the most violent tornadoes. Structures must withstand a 15-pound wooden beam launched at 100 miles per hour to qualify. In 2003, a monolithic dome in Missouri survived a direct tornado strike, while neighboring homes were reduced to rubble. 2 years later, in Biloxi, Mississippi, a dome weathered Hurricane Katrina's 155-mile-per-hour winds and storm surge without structural damage. Even in war zones, the design has held up. A dome in Iraq reportedly remained standing after a 5,000-pound bomb detonation nearby. The benefits aren't limited to disaster zones. A Wisconsin school district saved roughly $8 million in construction and energy costs by choosing domes over conventional buildings, thanks to dramatically lower utility bills and minimal maintenance. Securing a mortgage for a monolithic dome home often ends before it begins. Appraisers are required to find at least 3 recent comparable sales in the area. But dome homes are so rare that in most markets no such comps exist. Without them, banks cannot legally approve a loan, regardless of the building's performance or safety record. Emily Harper, a certified public appraiser, explains that federal guidelines force her to reject properties that don't fit the mold, literally. Even if a dome costs less to own and lasts longer, it's invisible to the system. Building codes add another obstacle. Many jurisdictions require a minimum 4 to 12 roof pitch, a standard written for shingle roofs, not seamless concrete shells. In California, permit offices sometimes demand a third-party engineering review for any non-standard structure, with fees that can reach $40,000 before a shovel even hits the ground. Each step, from appraisal to permit, quietly blocks domes from the mainstream. Housing that shrugs off fire, storms, and rising energy costs exists, yet policy, not physics, keeps it rare. As disasters intensify and affordability worsens, the real barrier isn't technology, but will. The future of shelter may depend on changing minds, not materials. What do you think?